All right. Well, welcome back.
Hello
So
everyone,
I'm
my name
really,
is Feline Hermans.
I'm really
And
excited to have Felin here with me remotely, and this was an interesting story a little bit because Felin actually just got off her plane. So where are you?
I'm in the Sydney airport.
All right. So we're gonna have a live talk from Sydney Airport. Um, so this will be. I'm really happy that your flight got there in time because this was a talk that I was really looking forward to. Um, so I think the story, you're going to explain the story at the beginning, right? So I'll
Yeah,
just switch over to your slides and we're ready to hear the story.
okay, I'm good to go, right?
Yep, good to go.
Yeah, let me know if anything is up with the audio because as Thomas said, I'm on airport Wi-Fi. You'll see people walking behind me, so it's a bit iffy. Welcome to this talk. I'm very happy I could make it anyway. My name is Felina. I'm assistant professor at Delft University of Technology where I research spreadsheets. But this talk is not about spreadsheets at all. It's about an evening in my life where I was playing the board game Quarto with my boyfriend at home. So it's not about spreadsheets, it's about Quarto. Here you see the game of Quarto. It's a little bit like four in a row. However, with four in a row, the pieces have two dimensions. They're white and black, or sometimes they are yellow and red. But with Quarto, the pieces have four properties. As you can see here on the screen, they can be white or black, they can be round or square, they can have a hole in the bottom, and they can be long or short. But the objective of the game is still the same. You have to get four in a row of one of the properties. So four black ones, or four short ones, or four square ones. So we were just playing this game a few times at home, and each of the time, either I won or my boyfriend won. So we were wondering, is it possible that this game ends in a tie? Is that a thing? So I imagine that in other people's lives in a parallel universe, people would be like, I don't know, I don't care, the end. But of course not in Nerdland, as you can imagine. We were like, let's figure this out. So we shoved the board game aside and we started programming, finding a solution whether or not this game can end in a tie. So what you can of course do, you can come up with this I guess, is you can brute force it. And the board looks pretty small, it's just 4 by 4, so why not? Well, if you do a little bit of offhand math, you will see that in the first field you have 16 possibilities, and then 15, and then 14, etc. And this goes out of hand quickly. This is 16 faculty, which is this number. And if you, for each of the assignments, so either way you put the pieces on the field, you have to do 160 checks because there are 10 ways in which you can get four in a row, 4 rows, 4 columns, and 2 diagonals. And then for each of them, you have to check for 4 properties if they are the same, so that's 16. So suppose you have MacBook Pro, like I have here, 2.4 gigahertz, 4 cores. Theoretically, you can do 10 billion tries a second, but still this would take 320,000 seconds, which is about 90 hours. And that's a bit long for a board game night. So the problem is not yet solved. We have to do something smart. And then I remember that when I was in university years ago, I actually had a course about this. I had a course on how to do all sorts of combinatorial problems using computers, using SAT solvers. So I was like, let's science the shit out of this. I know how to do this. I have the proper tools that could solve this problem. So the basic idea here is we're going to not directly solve the problem, go from the problem to the solution, but we are going from the problem to an alternative representation. And I will explain more what that representation is later. Then we will go in the alternative representation to a solution, and then we will go back to a solution in our original domain. And that might sound a little bit abstract to you, so let me give you an example of that. Suppose I have to divide this very big number, 78,974, by 2. So if I want to do that in the decimal system, it's lots of work. I have to do a number of calculations for each of the positions before I get my solution. But suppose I would transform this number into binary. I guess most of you will know how quickly you can divide by 2 if your number is in binary, right? You will just bit shift. You just remove the final 0 and then you have to divide it by 2. So that's very easy. And then, as I said, we have now a solution in the alternative problem domain. We still have to go back. We still have to go back to our original domain, the decimal numbers, but then we have our solution. So this is exactly what I'm going to do with SAT as well. This is my chosen alternative representation. I'm going to go from the original problem into an SAT world, solve it there, and then go back to the original. So what actually is SAT? What is this magical tool that you're going to use? You might be wondering. Well, it's all based on Boolean logic. And I guess most of you are familiar with Boolean logic, but let me quickly take you through the basics. So in Boolean logic, you can express propositions like this one. Do you want coffee or tea? And it will look like this, coffee and then sort of a V symbol or tea. And these propositions can be true or false. So in this case, coffee or tea is true because this guy says yes. You can also express conjunctions and. Do you want coffee and tea? That looks like this. That's the V flipped on top. The propositions can also be false instead of true, and we can negate them with this little hook sign. So not coffee and tea. Coffee and tea is not true. We can also negate variables, so not coffee. That's also a thing we can do. And if we have these propositions, we can derive more truth values from them. So if we know coffee or tea, not coffee and tea, and not coffee, all these things, we can conclude tea must be true. This guy really wants tea. These pictures, by the way, I have not hand drawn them, contrary to all of my other slides. They're by a wonderful lady named Sydney Padua, and this book is really, really amazing. You should totally all go out and buy it. It's a mix of history and mystery. It's really amazing. But let's go back to SAT solving. So the idea is you have such a Boolean proposition like coffee or tea, or like P or non-Q. And what we want to do in satisfiability problem is we want to find an assignment for these variables P and Q in such a way that it results in true. So for example, for P and non-Q, you can pick P is true and Q is false. Then you have P is true, or not Q, not false is true. So that's true or true, which is super true. And the good news is, if you have your problem in such a way, there are fantastic tools called SAT solvers that very quickly solve this problem. So what an SAT solver does is you give it something like this, like P or Q and non-R, and it tells you, yes, this is satisfiable. And most of the SAT solvers that are out there will also tell you how it is solvable. So it will say, yes, in such a way, for example, pick P is true, Q is false, and R is false, and that will give you true. The bad news is, though, that we haven't made our problem any simpler. If you know what it means, the problem is NP hard. And if you have no clue what that means the problem is very, very, very hard. So the idea is to use Boolean propositions to express the problem of quarto, to express how exactly a tie looks like. So what we can do for that is every field in our board, we can give it 4 booleans, which will represent what piece is on that square. And the 4 booleans will express the 4 properties. So for example, for one field here, we will say the first variable 030 represents if it's black or white. The second variable represents if it's long or short, square or round, and flat or whole. Yes, I said my. Is everything still okay? Because okay. Awesome. Yeah, I heard a little bit of rumor on your side in the background, so I just wanted to make sure. Okay, let's continue. So we have a variable per field, and if we have this, we can express exactly how a tie looks like. A tie looks like this. There is no row, nor a column, or a diagonal, for which one of these 4 properties is exactly the same. So it would look like this. For all of the properties, for all of the combinations, rows, columns, and diagonals, it cannot be the case that those 4 stones in the combinations have a similar property. So for example, it will look like this for one property, it should not be the case that 0, 0, 0 is equal to 0, 0, 0, 1, 0, 0, 2, 0, or 0, 3, 0. One more thing though, all the stones in the field have to be different. So it will be illegal for us to go to the toy shop and to buy a second quarto set and to make a tie with this. And the way one set is all the stones have different properties. We can also say no two stones on the boards can be the same. So for example, field 0, 0 and 0, 1 are not exactly the same. That means it's not the case that for all the four properties are equal. And of course, I'm not going to type all of these rules in a computer. I don't always use SAT solvers, but if I do, I generate the input file. It won't be fun to express all those rules and type them by hand. So what I did is I wrote a little C# program that loops over the properties, makes the rules, makes the diagonals, makes the columns, and then also adds a rule that the stones are not all the same. So that outputs something like this. So we have our problem solved, right? We have all the rules, we have exactly expressed how a tie looks like, so now we can solve with using an SAT solve. However, you might wonder, and maybe you were wondering this for a while, why is this better? How is it helping that you have converted your problem to SAT now? So let's look a little bit at what happens in the inside. What exactly does an SAT solver do? So the basics is really simple. What an SAT solver does, it is just trying all options. So if you give it this P or Q and non-R, it will do this. 0, 0, 0, that's not working, etc. until it finds an assignment that satisfies the whole proposition. However, of course, this is basically just brute forcing. This won't be quicker than doing a brute force. So it's a little bit more complicated than trying all options. There's this one trick that SAT solvers hate because it greatly reduces state space. This trick works as follows. For example, if you have an expression like this, P or non-Q and Q, you can derive from that. It's equi-satisfiable, just as satisfiable as P. So why is this the case? If you look closely at this proposition, you see that it consists of two parts, P or non-Q and Q. So something and something must be true. If that is the case, then both of them must be true. So we know for a fact that Q must be true. That means that non-Q is false. And that means that because P or non-Q has to be true as well, because it's one part of the... And P must be true too. And this is called unit resolution, and it greatly reduces state space. And I will show you in a few slides in an example how it exactly does that. This proof, by the way, is, as we professionals call it, a proof by hand waving, but you can actually prove this for the general case. So if you're very interested, here's some homework for you to prove after this session. Even if I'm off duty in the weekend, I'm still a professor, I'm still handing out homework. And actually I gave this lecture once and someone tweeted me the answer back, tweeted me a picture of a handwritten proof. So I have great hopes for you that at least one of you can do it too. So let's look at how unit resolution works. I have an example here, and you see that I have written it down in a little bit funky way. So every line is a part of a conjunction. So everything on line 1 has to be true, and everything on line 2. And this is a little bit easier for what I'm trying to show. So as I said, we're simply trying all options. So let's just pick one variable. Let's say the first one. Let's say P is true. So P is true, I marked that with green, that's, I guess, obvious. And the non-P's now are true. So now take a very close look at line 3, clause 3, non-P or non-S. Because non-P has already failed us, non-P is false. And this is non-P or non-S has to be true because it's together on one line. We know that S must be false to make non-S true. So we assign that and we propagate that, so the S's are now false. And now, unfortunately, there's no free lunch anymore. None of the rows have only one variable unassigned. There's no variable that is forced to be false to save the day. So again, we just pick one. Let's say we pick Q is true. There we go. We set Q to true and non-Q then, by definition, will be false. And now again, look at clause 4. R must be true to save the day because all of the other variables in this clause have already failed us. And there we have an assignment. So out of the 4 variables in the whole proposition, we only picked 2 and the other 2 were deduced. So if you visualize mentally the whole tree of possibilities, we sort of pruned half of the tree and that makes it a lot quicker. So you might wonder, yes, but that was a very nice example in which everything went right. What happens if you assign the variables in such a way that you get a conflict? That's a good question. Let me answer that for you. So here's the situation again. We pick P is true. That means all the non-P's are false. And now if you do unit resolution, you see that it cannot be true because either we pick S and then non-S is false, or we pick non-S, S is false, and then non-S will be true, but S will be false. So we have a conflict. Very sad, very conflict, much false. That's not what we want. So what we do there is we flip the last assignment. So the last thing we picked, which is not S because that's what we derived, the last thing we picked was P, and we simply flip it. We just say, okay, well, apparently P was not meant to be true, and we're going to flip it. So a second trick that I want to share with you is called watches. A second trick that you can use to make SAT solvers a lot quicker. And watches work like this. If you pay close attention, and I mentioned it a few times already, is that you can only do unit resolution if all variables except for one are unassigned. So for a few clauses, it's very easy to see. If you only have 5 lines, it's easy to see where to apply unit resolution. However, in realistic programs, you will see what is generated from my Quarto solution later. These can be millions, hundreds or millions of lines of variables. And then it's very expensive, you can imagine, to go through all of the lines to see if there's unit resolution possibility somewhere. So, as I said, we can only use it if all but one variable is assigned. So, if I can point at 2 unassigned clauses per variable, per clause, 2 unassigned variables per clause, unit resolution is impossible. So let me visualize that for you. Again, we're doing this. We pick P. P is true, and that means non-P is false. So I'm pointing here at 2 variables. I'm making the watches purple, so I know there are 2 unassigned variables. That means it's impossible to do unit resolution there. That leaves us with clauses 2 and 4. I cannot point at 2 variables there. Oh, let me go back. I cannot point at 2 variables there because there are no 2 unassigned variables, and that means I can do unit resolution there. Watches are watching unassigned variables, 2 of them. So that pointing is exactly what watches do. You don't watch all the things, you watch just 2 things, and that makes it a lot cheaper. So what happens if variables are assigned? Suppose we assign a variable. So in this case, we have assigned S. That means those S's, those purple dots I had on S, have to move now. So we just move them, can be to a random variable. So here we move S to R and here we move S to F. And if that movement is not possible, that means we can do unit resolution. There we go. So you might think, how is this so very useful? It's just pointing at 2 variables. It's basically just sort of a cache of where I can do unit resolution. So the really, really smart thing, it's so smart, I wish I had invented it, is that watches do not move if there's a conflict. When we backtrack, the watches can stay in place, sort of by definition. Because watches point at unassigned variables, if we backtrack, we won't make any changes to variables that are not assigned yet. So suppose, again, we have the conflict situation like we had in the previous, or actually in the same example when I explained unit resolution. We're going to backtrack. So we flip P and we remove the assignment for S. We can leave the watches where they are. because they were pointing at unassigned variables. And that makes it very, very quick, because you can imagine if you have lots of variables, there will be lots of backtracking. It happens that you make a wrong decision, but you can just leave the watches where they are. Okay, so now you have a good understanding of how an SAT solver works. And I have explained to you how I'm going to express my quarto problem in SAT. So we should be there, right? Well, if you pay close attention to the rules that I have generated with my C# program, you will see that they don't really look like something that an SAT solver uses. In fact, my problem is not solved yet. These are the rules I generate. However, this is what an SAT solver wants. It wants to have the conjunctive normal form. That means exactly like I showed you in the examples. Every line only has disjunctions, only has ors, and all the lines are combined with only ends, the conjunctive normal form, as this is called. So unfortunately, we are not yet done. We still have to transform the rules that we have generated to CNF. So this is, maybe you've been waiting for it, this is actually where F# comes in. If you just do a few loops, C# is fine, but for heavy duty, easily, you need F#. So what I did is I made a little type called term that expresses all the things I can have in a Boolean proposition. So a variable that has a string as a name, a not, an or, an and also true and false, that are operations we need in a simplification. I didn't include an equal in my language. I just directly rewrite that to an and or an or. That's just to make my language a bit easier. So what I do now is I express a number of equivalencies, a number of rules I can use to simplify the proposition I'm going to put in the SAT solver. For example, N, A, and true is equal to A. If I already have true, then A is the only thing that matters if I have it together in an end. So what I do then is I use a number of rules that can make any proposition into CNF. For example, I remove double negation. I apply De Morgan, which means that if I have negations on the outside, I push them in, because negations in CNF can only occur at the variable level. And I distribute ors that are at the outside level. I push them in, and that means I get an and on top. And I can apply both of these two rules until I reach a fixed point, until nothing changes anymore, and then guaranteed I will have CNF. This all is online, by the way. So if you have your CNF problem, if you want to express it, simplify it into a way that an SAT solver can write, then go to my GitHub and download it. So what you can do with my little language, let me show you how it looks like. You can define a nice term like this, so that looks somewhat human readable, or not A, B, or not A is equal to B, or not B is equal to C. So I can express that, and then you see that already something happens because I'm immediately rewriting the equals. And what I can do then is I can ask my program to immediately transfer it to Dmax. And Dmax is the format that all SAT solvers use. And it's not just CNF, as you will see now, it's even more tricky than CNF. There we go. This is what comes out of it. So you get, this is the format, PCNF, that's how it's supposed to be, and then you write down the number of clauses and the number of variables and the number of clauses. And then for each of the variables, very conveniently, they all have to be integers and cannot be strings. And then a minus means the negation of a variable, and every line has to end with 0 and a line break. Why? I don't know. A normal line break is not enough for SAT solvers. They need a 0 and a line break. So you can, without any extra effort if you need it, you can just use my library and you get exactly the input for the tool. So let me show you how that looks like on our Quattro problem. You see there are 46 variables and 4,160 clauses in this example. So you see that you can imagine that doing a unit resolution on all of the lines all the time is very costly if you have 4,000 lines, and this is not even that big of a problem. So there we are, right? So go back to my board game night. I've been programming for a few hours. I've made my solution. I'm going to put it into the SAT solver. So this is an exciting moment. Is it equal? Can it end in a tie? And of course, you're never really sure then, you haven't made a problem in your coding. Maybe you made a mistake. So let's see what happens. Here I type minisat. Input, there it is. And this is not edited. This is actually a video of me doing it. It's that quick. Maybe you missed it because you blinked, so let me go back. Let me show it to you again. There you go. Minisat input, bam! It is that quick. So by using science, we've gone from 90 hours to 2 seconds. So that's really, really cool. So what we want now is, okay, it is satisfiable. That's the answer you see all the way at the end, satisfiable. That means, yes, it is possible that there's a tie. But it would be nice if we can also have an example of a tie, just again to make sure that we didn't make a mistake in how we coded the answer. Yes, it is satisfiable. That is awesome. So we want to go back to the solution. There we go. We can ask Minisat as well to provide us with an output file. There we go. Now we have an output file, and this is actually how it looks like. Again, a very nice readable format. All the variables that are true are normal, and all the variables that are false have a minus. And actually we have to go down a little bit because of the way I coded my variables. So here you see that some variables are true and others are false. You can parse this back, and actually in an updated version of my library, I have parsed this back into a nice readable format. However, at this particular game night, I was sort of sad with programming at this point, so I just did it manually. You see here my scribbles on the paper, and look at that. That is how a tie looks like. Isn't that awesome? Of course, the next question now is, how many of those ties are there? Is it possible? Are there maybe 1,000 or 4,000? And that is also something you could do with an SAT solver, but that's something for another talk. And as I said, all this code is on GitHub. So you might think, okay, well, that's very nice. You can solve board games with SAT, but there are also very nice real-life applications that you can quickly solve with an SAT solver. For example, if you want to divide people in groups, and there are some constraints. So for example here, B loves A very much and B loves E, but B doesn't really care for C, and C and D also don't really play well together. So suppose I want to divide these people into groups. Let's say I want 2 groups. I can give each of the people a bit, just like 1 bit, and then I can express the bit of B should be equal to the bit of A, but the bit of B should not be equal to the bit of C, etc. And of course, if you want more groups, you can just give people more bits. And this very easily generates to planning and scheduling. There are even scientific papers that explain how you can use SAT solving to do efficient basketball scheduling. Another real-life example of an SAT solver is to decide if 2 processes are the same. So suppose I have here a specification robot that says a minimum is if I put in 0, 0, I get 0. If I put in 0, 1, I get 0, etc. And here I have an implementation robot that says, okay, if A is equal to B or B is false, then A and else B. So is this the same? We can use SAT solving. We can do that by, for every given input, all the possibilities, we just express that the outcome of A is equal to the outcome of B. And this is normally done on a fixed set, a finite set of inputs, because for these machines, you know what can go in. If you have infinite possibilities, it's of course a bit hard to enumerate them. And this really nicely generates to testing, specifically hardware testing, is where this is commonly used, but also DNA sequencing, where biologists want to know if 2 strings of DNA are the same or not, and you can also express that in a similar way. So that's it. That's everything I wanted to share with you today. Just in case you missed anything, you came in late, you are jet lagged just like me, let me briefly summarize the whole talk in like 1 minute. So if you missed anything, you can still get the gist of it. And if you didn't miss anything, this is of course optimal preparation to ask some questions. I hope you're all making notes and I can answer some. So what I wanted to do is solve the board game of Quarto. And I could do that brute force, but that is pretty slow. So what I did is I used some science. More specifically, I used SAT solving. And I explained to you what an SAT solver does. It uses unit resolution and watches to greatly speed up a problem that is otherwise MP hard. I made a little library where you can nicely express Boolean propositions that automatically generates for you the input to an SAT solver. I put it into an SAT solver and what do you know? Yes, it can add in a time. And I also showed you a few real-life examples, including scheduling and hardware testing, where you can use SAT solving for. So that's it. That was my talk. I will go back to Thomas now to see if there were any questions.
All right. Thank you very much for this. And I think we've probably lost your camera, or maybe we'll get it back. We'll see in a second. Oh, we've got your video back. Hey. Yeah. That was pretty extreme session. But anything's possible at fsharpConf, including a live talk from the Sydney airport. So thanks to you for an amazing talk. Thanks to our audience for being a bit patient when the sound wasn't quite right. But I think it was still really good. So let me see if we have any questions here. We already have a queue of questions for our next session. So I guess we'll have to go back to that in a second. So I do have one question. Is this how you play all the games you play?
Well, it's not how I play all the games. However, it is how I really like to play lots of games. So if I can pitch the F-Sharp Exchange in April, I will do another talk there about F-Sharp and games, because in September I'm actually competing in the World Championships of Computer Bridge with a program made in F-Sharp. So yeah, maybe I do like programming more than I like games.
So is there in the Quattro game sort of, is there anything about the game that makes it, like, because a computer can solve it really easily, is it a boring game, or is there anything sort of in the game specifically that we can learn from this experience?
Yeah, so there are games and more generic, there are situations where it's very easy for an experienced eye to see you can do SAT solving. So you see, if you practice this a little bit, you see that the pieces have 4 properties that only have 2 options. Then your nerd brain will be like, haha, brilliant! So obviously, games like Small World, that's a game I really like, where you have lots of characters and all the characters, lots of different properties, and there are lots of different phases in the game. That will be very, very hard to solve with an SAT solver. So the fact that this is a very abstract board game makes it a lot easier to solve. And I think the same would hold in a problem where you can easily point at things that are numbers or booleans. It will be easier to solve.
So I guess there's games that are sort of not easily mappable to the SAT problem. And then there are games where you could map them, but the state space would be so huge that you wouldn't be able to do anything with them.
Exactly. And there's one thing also I didn't explain about the Quarto game. There's a little twist, is that I pick a piece and my opponent places the piece.
Okay.
So in my simulation, to call it that, I've only determined whether it's possible to have a tie. Whether this actually happen if you have 2 players that play at their best capabilities, that is not what I tested. I've only shown it's possible, so I might need cooperation from my opponent to get this done, because he can see, if I pick that piece it will end in a tie, so I'm not doing that because I prefer losing over time, maybe. So if you want to do that, you need another technique called alpha-beta pruning, where you play the game from both sides repetitively, basically.
All right, I guess we'll have to leave the alpha-beta pruning to the next year's session.
I guess.
Sounds pretty good. But yeah, well, thanks again for joining us. It was really, really great to have you here. And hopefully next year we'll find you in some more friendly spot.
Yeah, but somewhere in an office without people running behind me would be great.
We'll see. We'll see.
See you!
Bye. And we will be back in a couple of seconds with David Stevens doing a Q&A. If you have any more questions that you would like us to talk about, anything you want to know about the Visual F# team inside Microsoft, then ask a question on Channel 9 Live, or we're monitoring Twitter as well, and we'll get back to you in a few minutes.